right, ladies and gentlemen, this is the background information about thermochemistry presentation. It's up to you how you choose to assimilate this particular information. You can certainly just look at the slides on your own. They're fairly self-explanatory, or you can listen to this video if you prefer Mrs. Julian's dulcet tones. And you can also look in the book. If you have a look at the slides, see what information is being covered. The book covers a lot of this stuff as well. But this is critical information about the foundations of thermodynamics as a whole that we simply don't have time for in class because while that's important, it's not stuff that relates as directly to chemistry as other things. So we reserve the in-class time for discussions of things that relate most importantly to chemistry. So first of all, we've got the definitions of thermodynamics and thermochemistry. And realistically, thermodynamics, the study of energy and its transformations, is for everything in the possible universe that relates to energy, which is quite a lot. Thermochemistry takes that and says, okay, what about the things that fall under this very, very broad umbrella that relates specifically to chemical reactions? So while we might say that friction is a way to generate heat, which it is. It's true. It wouldn't really fall under the banner of thermochemistry because you're not doing a chemical reaction to get that heat to form. Kinetic and potential energy. Now, this is something that I know you've had before in basic physical science classes in, say, middle school. Kinetic energy, which I'll abbreviate as KE, is the energy of motion, and the formula is 1/2 mv squared. Where m is mass and v is velocity. And I will add that when you're using this formula, the kinetic energy formula, mass should be in kilograms and velocity should be in meters per second. And you'll see why on the next slide if you don't already know. But it's basically saying kinetic energy, the energy of motion, it's related to both how much mass an object has and also the velocity of the object. So there is a distinction between speed, velocity, which is just meters per second, versus kinetic energy, which takes into account the mass of the object as well. Potential energy is stored energy, the energy an object possesses because of its position. The classic example of potential energy is if you consider you're holding up a book off of the floor, above the floor. That book has a certain amount of potential energy because it has the potential to drop and fall to the floor. It has energy that can be converted into kinetic energy. And if you were to move the book lower to the floor, it would have less potential energy because it wouldn't be capable of as much motion. It couldn't turn that energy into other things, into as much motion as it when you held it up very, very high. So the potential energy tends to increase in terms of that very simplistic explanation. Now, potential energy for us, when we're talking about thermochemistry, becomes important because potential energy is stored in chemical bonds. We'll talk a lot more about that when we do our bonding unit later in the year, but bonds are essentially little energy banks that if they're broken, all this energy sort of spills out and has to affect the things around it. Potential energy can be converted into kinetic energy. Example, dropping a ball off a building. If you're holding a ball at over the roof of a building, overlooking a sidewalk, you would have a tremendous amount of potential energy, tremendous amount of potential to turn its position into speed. And this, again, relating this back to chemistry, chemical bonds which store potential energy can be broken, and the potential energy there can be converted to other types of energy. Heat is really the big one that we're looking at. Units of energy. The SI unit of heat, a unit of energy, is the joule, and SI is essentially the modern version of metric. And the joule as a unit comes from the formula for kinetic energy. This right here is actually the definition of a joule. And you'll notice that in the definition of a joule, we have kilograms per meter squared, or kilogram meter squared per second squared. because this is what a joule is when we're using the kinetic energy formula, that's why mass has to be in kilograms, velocity has to be in meters per second, because we're going to be solving for something that is joules, and joule is defined in terms of this way. Now we also have calories. Calories are another very, very common unit of energy, and the conversion between the two is shown here. No, you do not have to use it. I would never ask you to use it. And in terms of science, chemists argue about which unit of energy they prefer. In this class and in most introductory classes, almost all introductory classes, you'll be using the joules, but organic chemists really like calories, and so you'll see if you go into organic chemistry that a lot of the discussion of heat will be in terms of calories. So they're both used. They're both used in science. This is the same, well, it's related, this is similar to the same calorie that we see on food packages. It's not the exact same one because the calorie that we see in food packages is actually a kilocalorie, which you'll notice what we have the capital C, that's how it's denoted, not the lowercase c calorie. The universe. The universe is a good topic for discussion for us. Is fundamentally divided into two parts. I shouldn't say halves because it's not divided in half, but two parts, system and the surroundings. And whenever we're talking about thermochemistry, that's really, we have to have these two distinctions, system versus the surroundings. The system is whatever part that you're concerned with. What are you studying in this particular question? For us, it's going to be a particular chemical reaction that has some sort of transfer of energy. That is the system. That is what we are interested in. The surroundings is literally everything else in the entire universe that is not the system. It's important to note, and I'll throw these definitions up here as well, it's important to note when we're talking system versus surroundings that the whatever glassware is used to hold the reaction is part of the surroundings and not the system. And typically speaking, aqueous chemistry reactions, the water that is surrounding the chemicals that are reacting is not part of the system. It's part of the surroundings. And when you measure the temperature of aqueous chemistry reactions, you're actually not measuring the temperature of the reaction itself. You're measuring the temperature of the surroundings. You're measuring the temperature of the water that is surrounding the aqueous chemical reaction. And you have to sort of bear that in mind when you're thinking about what that temperature reading is telling you. Exothermic reactions release energy from the system to the surroundings, so energy leaves the system and goes to the surroundings, and endothermic reactions are the opposite. Endothermic reactions absorb energy from their surroundings so that the system shows a net increase. Transferring energy, so that's the basics of sort of directional stuff. Now, force. We don't talk a lot about force in here, but it's worthwhile sort of understanding the basics of force, because force is a type of energy as well. Force is defined as a push or a pull, and work is the amount of force applied to an object over a distance. I'm sorry, work is a form of energy. And we have an equation that can actually calculate this. Work equals force times distance. Physics people, you've undoubtedly seen this before. If you're not in physics, this is sort of the basics of work and force. Heat. Heat is distinguished from these. Heat is the energy transferred from a hotter object to a colder one, and it is a thermal energy, typically speaking. And energy is simply the capacity to do work or to transfer heat. So that's why we talk about work, why we talk about force, because it is a form of energy, and heat is an alternate form of energy. Energy is defined as basically, can something do work, or does it have to have work done on it? Can something transfer heat, or is it going to absorb heat? If so, we can talk about it in terms of energy. Now, the example, we're going to talk a lot about heat. That's really the big thing that we're interested in terms of chemistry. We're interested in the thermochemistry of a reaction, the heat exchange because of a chemical reaction. But in terms of work, you can also consider aspects of chemistry to have an effect on overall thermodynamics because of their capacity to do work. And sort of the classic example of this is gas in a steam engine. If you heat up the gas will start to move in a piston. the gas will start to move faster, and it will start colliding both more frequently and with a higher speed with the piston. As the gas expands, it comes into contact and it has molecular collisions with the piston, thereby expanding the piston and doing work on the piston. So we do have, this is sort of the only time that we'll really discuss the work because of things that relate to chemistry, because gases are definitely a big component of chemistry. But it's, it is always there. You can take something that you know about chemistry and have it perform work on a system. First law of thermodynamics. What I think is interesting about the laws of thermodynamics is that while they definitely say very specific things, we kind of interpret them, we sort of pull from them what they mean as it relates to chemistry. So if you ask a physicist, what are the big points of the first law of thermodynamics, they might tell you something different than when you ask a chemist what are the big points of the first law of thermodynamics, because they're each sort of pulling from the first law what really applies to their particular discipline. And the first law of thermodynamics states that the energy of the universe is constant, aka the law of conservation of energy, that energy is neither created nor destroyed. Now, Q, what is energy? It's the capacity to do work or transfer heat. So heat is Q. Symbol for heat is Q, because of course it is. It makes total sense with the word heat. And W is work. And delta U is what's frequently referred to as the change in energy of the universe. And this right here is the summing up of the first law. If you were to write out the first law of thermodynamics in terms of a chemical formula, not a chemical formula, but just a mathematical formula, this is what it would be written as. And whenever we're talking about any sort of ultimate change or transfer of energy, we always want to take the system's point of view. So you're always looking at the system. Was the system, what changed for the system? Did the system do work or have work done on it? Did the system absorb heat or gain heat? So whenever we're looking at this, we're taking the system's point of view. And I will also add that we can substitute in delta E for delta U. Whenever we're basically, this is how chemists interpret the first law of thermodynamics, that we can take this idea that the universe's energy is unchanging and say, well, okay, this idea of heat and work, it also will apply to a system as well. Not necessarily that the system's energy is unchanging, but we can take this concept of heat and work, heat entering, work being done on something, and apply it that way. Now, exothermic, just sort of looking at this pictorially, exothermic reactions. This is just a general graphic showing an exothermic reaction, not exothermic necessarily in terms of heat, but just exothermic in terms of energy, losing energy. So we have a system that is losing energy to its surroundings. Surroundings on the outside of the rectangle system is everything that's inside the rectangle, and we've got energy moving from the inside to the outside, showing overall a net loss. A net loss of energy by the system. Because of that, we say that for exothermic reactions, a loss of energy, delta E, is less than 0. Delta E is negative, a negative sign, because the system, when the whatever reaction or process finishes, it contains less energy than it began with. Now, the universe as a whole, energy has stayed the same, but it is transferred from the system into the surroundings. An example of this shown below is this methane plus oxygen. The combustion of methane makes carbon dioxide, water, and heat. Exothermic, showing the loss of energy right there, the fact that heat is a product. And if we consider the alternate side, we've got now system and surroundings, but this is endothermic. So in an endothermic reaction or process, I don't want to use the term reaction because this is broad speaking, doesn't have to be chemistry. Energy goes from the surroundings into the system. So what we have is a net gain of energy by the system. The system took in energy from the surroundings in either the form of heat or work, and therefore delta E right here, delta E is positive, showing a gain in net energy by the system. That's what I mean when we say we take the system's point of view. The system has a net gain, surroundings is a net loss. And representing this in terms of chemistry, heat is a reactant, indicating it that way. Now, we're going to talk more about potential energy diagrams when we get to kinetics, but I do want to add that potential energy diagrams are representative of these exothermic endothermic reactions. So this overall shape should look familiar to you. This is the same reaction as shown previously. We know it's exothermic because heat is a product. And if you remember about potential energy diagrams, they have the beginning of the reaction, the middle, and the end. And what this is showing, because we have potential energy on the y-axis, is saying that we're starting at a certain amount of energy that's up here, and then the reaction happens, and then we're ending at a lower amount of energy down here, aka delta E is less than 0. Delta E is negative. It lost energy. It has a net loss. And then if we look at the opposite one, the endothermic reaction, we see the same sort of thing. Potential energy is on the y-axis, the reactants on the left, the products on the right. This is endothermic, and this is showing a net gain of energy. Heat has come into the system. We went from low energy to high energy. The reaction gained energy. In terms of heat, endothermic and exothermic still apply, most definitely. Endothermic, the heat transfer is viewable as positive, a net gain of heat by the system. Exothermic heat transfer is viewed as negative, a net loss of heat by the system. So you're taking the system's point of view. Did the system gain heat or lose heat? But what I really want to mention is this. Similar rules for work. Hopefully you're used to this concept of heat as either coming in and being positive, you gained heat, or going out and being negative, aka you lost heat, exothermic. But you can see, and you should see, work as being the same way. Is work entering the system? If so, then it would be a positive gain of energy in the form of work. Or is the system doing the work? Is the work leaving the system? In which case work would be negative. It would be like an exothermic reaction. And I honestly, because I am a chemist and because I have a chemist's brain, I think of it in these terms. Is work given off or is work absorbed? Physics people would laugh at me when they say this, when they see this, but that's the way my chemist brain thinks about it. Is the system putting work from itself to the surroundings, aka is it doing work on the surroundings? Is it giving off the work? Or is it having work done on itself? Is it absorbing work from the surroundings? Do the surroundings have to do something to the system? Is the system taking in the work? And we have the negative versus positive ways of looking at this, right? This is negative, this is positive. If work is given off, if the system does work on the surroundings, then work W is negative. If the system has to absorb work from the surroundings, then overall work is positive. I'm going to stop here because the first lecture, we're at just shy of 20 minutes, is just for the basics, and then I'll have a second one when we get to calorimetry specifically, some basics there.